Hello friends, so this is the last topic, that is tracking radar. So basically tracking radar is like we can see with basically this will track, right? So track an object, that means it will only fix to a object and it will move accordingly, so like that. So these are the two examples of missile range precision instrumentation radar that use monopulse angle tracking. Both operates at C-band. Top fixed site AN or FPQ-6 precision tracking radar with a 29 feet diameter cross-grain reflector antenna. So, and we already see what is this cross-grain reflector antenna in my radar antennas, and capable of 0.1 milli tracking accuracy. Button mobile AN or MPS-39 multi-object tracking radar motor, multi-object tracking radar MOTR. A trainable space fed 12 feet diameter electronically steerable lens array antenna, sorry, lens array radar. So electrically steerable, it can rotate radar for simultaneously tracking up to 10 objects to a radar accuracy of several feet and 0.2 milli angle accuracy. So what is the tracking with the radar? So a radar not only recognizes the precision of a target, but it determines the target's location on its range and in on one or two angle coordinates. So radar can observe the target over time and provide trajectory or track and predict where it will be in the future. It can also predict the future path where it will go. Types of radar that are that will provide the tracks of targets. Single target tracker (STT). This tracker on radar is designed to continuously track a single target at a relative rapid faster data at relative rapid, that means fast data rates like 10 scans per second. Military missile tracking, basically it is an application of military missile tracking. The antenna beam of a single target tracker follows the target by obtaining an angle error signal and employing a closed loop servo system to keep the error minimal, basically error significantly small. Okay, so what happens when this target is moving, for example, uh, so for example the target is moving like this. If the tracker is targeting here, after some time this object has moved to here, that means there is a slight error, right? So it will automatically, actually, it will have very high accuracy. That small variation will able to rotate. So basically that small variation in the angle will be given as a feedback to it, and that will rotate. That is the servo system. So a small angle error signal means that the radar is accurately tracking the target. Automatic detection and tracking, ADT. So ADT performs tracking as part of an air surveillance radar. For example, civil air traffic control. And civil air traffic control is like aeroplanes and all in the airports you will see, right? So in that display, they will see multiple airplanes in the vicinity. So where that airplane is, like that. The rate at which the observations are made depends on the time taken by the radar antenna to complete one scan. Basically, in example, 1 to 12 scans per second, low rotation rate, basically. It has advanced over STI, single tracking, single tracking, single target tracker, and it is automatic detection and track. Okay, and STT, that it can simultaneously track a large number of targets. So basically 100 to 1000 targets. An advanced, okay, and tracking is done open loop tracking is done in open loop. In that the antenna position is not controlled by processing tracking data as it is in STT. In STT, what happens that the change in angle will be taken as a feedback and it will move in the server system, right? But this will not happen in this ADT. uh, Phased array radar tracking. A large number of trackers can be tracked with a high data rate by an electrically sterile phase array radar. So basically, there will be array of antennas and can be steered phase array. Basically, phase array, we can see what is an array antenna. So in my radar antennas, video, we can see that all types of radar antennas. And wait, I think I'll show you. Like, so basically, let us take a simple parallel field. There will be one antenna like this with a delay phi, and again it will be having some delay of 2 phi maybe. So all this, like, it will be an array. Okay, all this will be connected in parallel and all. So this will be parallel field. So each one will have a different phase. So which will basically there will be phase device that will change the phase of this signal. Basically it will in turn rotate the signal in the particular direction. Okay, that is what steered phase array, electronic steered phase array, and it combines the rapid update rate of a STT with the ability of ADT and hold to many targets in tracking. With the ability of ADT, basically it will use all the single STTs only, single target trackers, but which actually there are many trackers, right? That's why it can be able to, it has the ability of same ADT, how it can track multiple objects. Track while scan, TWS. So TWS radar rapidly scans a limited array sector to maintain tracks with a moderate data with a what you call medium, like, okay, moderate data rate on more than one target with the coverage of antenna. So in this track while scan, it will scan rapidly in a limited area sector, or in this small sector it will scan rapidly, and in the different sector it will scan rapidly, like that. So on more than one target it can detect by using this coverage of the antenna, depending on the coverage of the antenna. Okay, so basic principles of continuous array angle tracking. These are the two, and the two overlap antenna patterns that cross over the bore side direction theta naught. A target is located in this example to be to the right of the bore. Okay, a target is located in the example to the right of the bore side of the antenna theta t. Okay, the target is somewhere this side. This is the center and this is the right. Which indicates that two beams. Both side of theta t. The amplitude of AB of a target echo in the beam B is larger than the amplitude of A in the beam A, which indicates that the two beams should be moved to the right to the bring the target to the broadside position. So when you observe here this point, and if you observe this point, we can see that actually see, this is the other point, right? This is the actually the target is present in the right side. If you observe, when basically there are two pulses, okay, two echoes. One has an when the target is present in this location, in this TT, basically, okay. The location is when this target is located on the right side. One echo signal has an amplitude at this particular theta is this value A, but for the B echo, the amplitude is at here. So basically what we can say is which echo has the higher amplitude at that particular theta, that side it should rotate. So that side the target is present. So in this case echo B has the more amplitude than echo A, because echo is on the left side and echo B is on the right side, and the target is also on the right side. That's why echo B has the higher amplitude at this particular theta t. Okay, so that from that we can say that the target is on the right side, and okay, B is larger than the amplitude, which indicates the moved on the right side. Okay, broadside position theta net is shown in the location in the direction of the target theta t. When so what happens now, this will move, the radar will move to this theta t. Basically it will move to the theta t, and it will see that when both these A echo and B echo will have the same amplitude, that means it is in the right angle. Like that it will check. If the target is on the left side, it will the A will have the higher amplitude, then it will move towards left, and it will check whether this it is moved correctly or not by again seeing that both amplitudes, if both amplitudes at this point are equal, then it will make sure then it will get to know that I am in the right path. Monopulse tracking. So this is a simple block diagram of a amplitude compressive monopulse in some angle coordinate. Sigma denotes the sum channel, delta denotes the difference channel. So here we can see there there is one sigma and delta, right? So basically what is happening, so a simple block diagram for a amplitude compensation monopole in one angle coordinate. Sigma denotes the sum channel, delta denotes the difference channel. Okay, so there is a transmitter, this will go to the mixer, and the sum channel here it will go into the IF amplifier. Okay, so and this is the antenna. Basically this transmitter will, actually this is transmitter, and this from this letting splitted. Okay, this is some channel, and this difference channel will go into this mixture actually. So basically this is the this half is the sum channel, and this is the difference channel. Okay, so both mixtures will have the same frequency, that is local oscillator frequency. And what happens, this is the transmitted part, and this basically it is the same replica, mixer and IF amplifier and mixer and IF amplifier. But what happens here, basically when the transmitter and this is the receiver, kind of receiver, let us take it like a receiver and this is the transmitter. So it will check for the phase sensitive error detector, basically phase sensitive detector. So depending on these two signals, it will check the angle error signal, and amplitude detector is the range angle. So basically in this above figure we have seen that one will check the point which is high and low, that's what. Okay, and depending on the error, how much small error, it will rotate, so like that. So monopole tracking, a monopole tracker is defined as one in the which okay, monopole tracker. A monopole tracker is defined as one in which information concerning the angle location of a target is obtained by comparison of signals received in two or more simultaneous beams. A measurement of angle may be made on the basis of single pulse, and hence the name. Okay, the measurement of angle may be made on the basis of a single pulse. That's why it is called monopulse tracking. By making an angle measurement based on the single signals that appear simultaneously in more than one antenna beam, that the accuracy improved. Okay, so we are using more than one antenna beam, right, to check to verify. Here we are checking two beams, so that's why the accuracy get improved. And block diagram, in the block diagram, the two adjacent antenna feeds are connected to the two input arms of a hybrid junction, which has two input ports and two input ports and output ports. When two signals from basically it's output, sorry. So when two signals from two squinted beams, you remember the squinted beam concept where there are two beams, right? This is there will be a circle like this is radar, this is a beam B, and one more is like this beam A, right? So this is what we call as splitted beams. Their splitted beams are inserted at the two input ports, and the sum and difference of the two are found at the two output ports. Basically it is like a H bridge. In my RF videos you can see, hybrid T, where it is a 4-port device which has two input ports and two output ports, where so basically there will be 4 ports, will give the input, and from two that other two are, one is summing port and other is the difference port. So conical scan and sequential lobbing. So canonical scan and sequential lobbing, monopulse tracker utilizes multiple fixed beams to obtain the angle measurement. Okay, but sequential lobbing uses single antenna on time shared basis in sequential manner to obtain the angle measurement. So basically in monopole tracking what it uses multiple fixed beams like A, B, like you as we see previously, fixed beam to obtain an angle measurement. But in sequential lobbing uses single antenna only. Okay, in the previous name it is like monopulse tracker. That means only one pulse is generated, but they are not telling us how many antennas are there. Here in the sequential logging, use only single antenna. On time share basis, the sequential manner to obtain the angle measurement. So here the lobbing switching antenna pattern and the error signals for one angle coordinate. Polar A is the diagram for polar representation of a switched antenna pattern, and B is for rectangle representation. Okay, and C is the error signals. Okay, for example, here this is the first beam and this is the second beam, but the target is present somewhere here. Okay, what happens? The reference line is somewhere here, and it is towards the, when you draw a reference line here. So when you take this and so it's somewhat here, right? So this target is towards the right side. That's why the amplitude of this beam 2 or the dotted line will be higher, right? So this point will be higher compared to this one. So then like we can use that the same way. Basically this is the same representing in rectangular representation, where this is the center angle and the target is here, so it will switch to the position 2 like that. Okay, and again it will compare where the target is. If it the theta, that reference line and the target line is matching, it will like that, it will conclude. Okay, if it not matches, it will send that error how much error the angle is, like that. Okay, so the difference in the amplitude between the voltages obtained in the two switched positions in a measure of the angular displacement of the target from the switched axis. So first it is in which beam which is the amplitude higher, it will switch to that side. Okay, the direction in which the move the beam to obtain the target broadside, or basically I told broadside means which side is that, on the if it is on the right side or left side, is found by observing with the beam position has the target signal. When the echo signal is in the two beam positions are equal, basically this is what we have already discussed. Basically there are this one, right? One is here and other beam will be like this. If the target is located here, that means like this, right? But the reference line is this one, theta 0, and this is theta target. Since this might be somewhere not like this, I'll show you the diagrams better. So this one here we can see, it will compare these two amplitudes, which is higher, and it will switch towards that side, and again it will check compare the this is the broadside. Broadside is the center reference to the broadside. Which side with respect to broadside, which side it is, that means it is either it is on the right side or left side. If the target is in the right side, by observing the amplitudes, which side the amplitude is high, then it will switch to it, and again it will compare with the broadside and the target direction. If it is if they both are equal, then it is in the correct direction. Okay, so the direction in which the moving the beam to bring the target to broadside is found by observing which beam position has the largest signal, that is what, largest amplitude. When the echo signal in the two beam positions are equal, the target is on the right and its direction in that is switching axis. So which side it will decide, and then it will switch to that particular direction. Okay, so conical scan tracking. So basically this is the same split angle. So once initially it is here, and one more beam is like for this is A beam, and this is the okay. what happens, this is antenna beam. Once it is like this and again it is rotate, so it will switches to this side. So basically two beams will be there, depending on which side the amplitude is higher, it will decide. Okay, like that. Initially the target is at here, for example, and initially the beam is located in that direction, again it is moving, and then what happens, it will also move depending on the error angle. The same way, this is the same way how I have explained this. Okay, how I explained this. This is in the rectangle representation, that's it. So this is the end of the course, radar. Thank you for watching, hope you like, share and subscribe.